All right, welcome to 12:06. Let me get the old iPad fired up here since we're going to need to use this. Oops, that's not what I wanted to do. That wasn't the right meeting. Personal meeting room. There we go. Join there. Get that here so I can use my iPad. And there, now you don't have to see me. I'm going to share my screen. And away we go. So areas of similar triangles. Make sure you have your textbook out because we're going to refer to a number of the problems there. The section starts on page 394. Okay, so what have we learned about triangles with the same height? The ratio of their areas equals that should be ratio, not the n should be crossed off, not the o, of their what? Their bases, right? Okay. So in other words, the area of one triangle over the area of a second triangle equals 1/2 b1 over h over 1/2 b2 over h. Cancel off the 1/2s, cancel off the h's, right? Because they have the same height. And that leaves the ratio of their bases. Okay. So let's look at another theorem here. And this theorem says that if two triangles are similar, then the ratio of their areas is the square of the ratio of any two corresponding sides. So one way to think about this is area of one triangle over the area of second equals ratio of their sides. Remember, all sides are going to have the same ratio, all corresponding sides, right? We just have to square it. It's all because they're similar triangles, okay? If you look at page 395, might want to get that out. I know you've read this already, but that page kind of goes through the proof on it. So I would suggest that you look through that. I don't think we'll take the time to go through that here right now. But if you have questions on it, please ask me and we can definitely go through it together. Okay, so, but what we're saying is that the ratio of the areas of the similar triangles is equal to the square of whatever the ratio is of corresponding sides. Now, think about it. If we took the square root of both sides of this, then one another kind of use of this, or another thing that we could say, is that the ratio of the sides is equal to the square root of the ratio of the areas of the similar triangles. Yeah, obviously we can't. So these kind of work together. I feel like putting an 8 or a turned infinity sign. They're linked together forever and always. How about that? Okay, great. Let's practice. So we're going to practice those. Okay, and again, I want you to try these on your own, and then you can always uncover when you think you've got it, or if you're unsure or whatever. Okay, so two equilateral triangles. Equilaterals. What does that mean? Oh yeah, they're similar. Have corresponding sides of 3 meters and 5 meters. What is the ratio of their areas? Okay, pause the video, give it a shot. All right, well, hopefully, since we know that the ratio of their areas is the square of the ratio of corresponding sides, and we have the corresponding sides are 3 and 5, we just have to square 3 over 5, which is 3 squared over 5 squared, which is 9 over 25. Yay, I hope got that one. Woo-hoo. Okay, awesome. They're going to get harder, I promise. Okay, let's look at number 2. Two similar triangles have areas of 256 square meters and 49 square meters. Oh, so nice of your math teacher to use those numbers. If one side of the larger triangle is 24 meters, then find that got cut off there, find the corresponding side of the small triangle, okay? So let's look at what we have again. We have similar triangles. We have an area of a bigger one and a smaller one. And we know one side of the bigger one is 24. We're trying to find the corresponding side of the small. Okay, give it a shot. All right, I'm back, so you can, here we go. So hopefully you set it up as 49 over 256 equals x, which is the length of the corresponding small side, over 24 and squared, okay? And by the way, you could have these flips. It wouldn't make a difference if you did 256 over 49, as long as you had 24 over x and then quantity squared. Take the square root of both sides, because what we're trying to do is solve for x, right? And if you do that, obviously you get 7 over 16 and x over 24 when you take the square roots. And then You can reduce this fraction. Remember, two denominators, you can always reduce them by a common factor if you want. A lot easier than cross multiplying, having to do with 24 times 7 and 16 and all that stuff. So much easier to reduce this down to a 2 and a 3 because 8 goes into both of them. And then we have 2x equals 21 when we do the old bow tie. Divide by 2 and you get 10.5 meters. Does that answer seem to make sense? Yeah, obviously we know it should be smaller, right? And a fair bit smaller based on the areas. Okay, great. All right, look at page 396. We're going to go through some of the problems here, starting with number 2. And I have these color coded. So the first thing we have to do, because we're doing this problem 3 times with different numbers. Number 2, it says, in the figure, angle A is congruent to angle A prime, and angle B is congruent to angle B prime. What is the ratio of the areas of the triangles if x is 5 and x prime is 7? Well, first ask yourself, by telling us that those two sets of angles are congruent, what does that tell us? Oh yeah, similar triangles, huh? Okay, so 5 and 7. So we're using 5 and 7 there. So why don't you figure that one out? And again, we're trying to figure out what is the ratio of the areas. All right. So hopefully you did 5 over 7 squared and got 25 over 49. Because remember, the ratio of the areas of similar triangles is equal to the ratio of corresponding sides squared. Okay. Second part says if y is equal to 4 and y prime is equal to 3 root 3. Okay, so let's try that one. This one. Oh, no, I didn't. It was the other one. Oh, well. This one. So 4 over 3 root 3 would be one way to, use would be how you'd set it up because they want the ratio of the areas of the triangles. So I guess if you had it the other way, that would be all right, I guess. Yeah, because they didn't really say which comes first. So if you had done, 49 to 25, 27 to 16, and 9 to 5, that would have been fine too. Okay. All right. So let's move on to number 4. Number 4 is a good one here. I like this problem. This is definitely a challenge problem, although probably not as much as number 5 is. I don't know. Maybe that's not true. Okay, so here we go. Number 4 says in the figure, the area of triangle ADE over the area of the triangle of ABC. So the ratio of the area of the small triangle to the ratio of the big triangle is equal to 2 over 5. Okay, A, show that the area of angle ADE, small triangle, is equal to 2/5 of the area of the big triangle. 2/5 of it. Okay. How would you do that? All right, let's do that. Just do the first part. All right, well, this is what we were given, right? Isn't this just a matter of cross multiplying? So 5 times area of angle ADE equals 2 times the area of angle of ABC. And then we're trying to get the area of triangle ADE by itself. So what would we have to do? Divide both sides by 5 and voila, there we have it. Okay. Okay, part B is a little bit more challenging. It's a lot more challenging, maybe. I don't know. All right, so here we're trying to show that the area of triangle ADE, the small triangle, is equal to 2/3 of the area of quadrilateral DBCE. All right, so see if you can figure that one out. All right, pause the video. All right, here we go. All right, wouldn't you agree with me that I did different letters, BCED, but whatever, that quadrilateral is equal to the area of the entire big triangle ABC minus the area of the small triangle ADE? Yeah, okay. Well, what do we know about triangle ADE, the area of ADE? We know it's equal to 2/5 of ABC. Right, so I can substitute in 2/5 of ABC for ADE. Can I simplify this? If I have a whole of something and then I want to subtract 2/5 of it, how much is left of it? Yeah, 3/5. Okay, so we have that the quad is 3/5 of the big triangle, but that's not what we needed to prove. We needed to show that the big triangle, I'm sorry, the small triangle was 2/3 of the quad. Well, isn't 2/5 the same as 2/3 of 3/5? Right? So if we know that the ratio of ADE is to ABC is 2/5, and the ratio of and that BCED is 3/5 of ABC, isn't 2/5 the same as 2/3 of 3/5? Yeah, it sure is. Okay, that was a good one. All right, last problem, number 5. We've got 3 parts to this one. This is where I need my iPad. All right. So we're given the figure, and we know that GHIK is a parallelogram. So let's mark that up, and we can mark that up. And well, I don't know if we need to mark those up. I think we can remember that. That might be easier if we remember it. But we know that M and H are, or N and M are midpoints, right? So boom, boom, and boom, 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 boom. Okay. All right. So A says that got to show that the area of GKN is equal to the area of KMI. Okay. All right. So go ahead and see. I'll give you one hint. One hint is you probably want to draw in KH, and then remember it's a parallelogram. All right. So here's how you do it. Isn't it true, and it might be easier to see this from looking at triangle KHI and KMI. Wouldn't you agree with me that the area of triangle KMI is half of the area of triangle KHI? And why do you think that is? Remember the formula of a triangle, 1/2 base times height. Okay. Same height, right? Same height for both those triangles, KMI, KHI. Think about it. Think about it. Same height, right? Same height to if we drew this down, right? And what do we know about the base? Yeah, it's half, right? It's a midpoint. Okay. So we know that KMI is half of triangle KHI. Okay. Same thing can be said for KGN. Triangle KGN is compared to triangle KGH. Okay. And what else do we know about parallelograms when we draw in a diagonal? Do you remember? Yeah. Did they form what? 2 congruent triangles, don't they? Yes, they do, which means they have the same area. So half of the same areas means that they are equal to each other. Ba-boom. Okay, B says, show that the area of GKN is over the area of the entire parallelogram is equal to 1/4. Okay, well, that's probably not that hard to show. If we know that KGN is half of KGH, that its area is half of it, right? And KGH is half of the whole thing because we know diagonal separates the parallelogram into 2 congruent parts. Isn't a half of a half a fourth? Yeah. Okay. And then the third part says, show that the area of KMI is equal to half of N of quadrilateral K or NHMK. Okay, so trying to show that it is half of this. Okay. And you probably can see that. We're comparing that to, here, I'll put this in yellow. We're comparing that to the area of KMI. KMI. Okay. So how would we do that? Okay. Well, if we already know that this and this are congruent, right? And we know that this is half of KGH, and this, KMI, is half of KHI, then doesn't that lead us to know that the area, what's left, which is inside the red, right, is going to be half of the entire parallelogram. Okay. All right. So just a couple of pretty challenging problems, but good ones there. Again, the main takeaway is these two theorems here, right? The ratio of the areas of similar triangles is equal to the square, not the square root, the square of the ratio of corresponding sides. And similarly, the ratio of corresponding sides in similar triangles is equal to the square root of the ratio of the areas. All right, congratulations, done with 12-6. Whoop, whoop, whoop. All right, see you later.